dots.
We can code our handwriting.
One is code, right? One is definitely
one is
code.
Oh,
Yeah.
okay. Okay.
Yeah.
I do the same. I do both. Okay.
How can you do both?
Total variance about the
Yeah, but that's how can you do both? You have to generate the prime motion, right?
not for John I mean science.
Sine? Oh, yeah. You could do the integral by hand.
Yeah.
That's true.
But
You should do.
I did both, so
Yeah,
I just
you could do
want to
both.
make sure.
Yeah,
Okay.
yeah. I think I meant for you to do the integral by hand because it's easier.
Yeah, but I did both. Okay.
Okay. Yeah. Awesome. Thanks. Maybe we'll make it full screen. Yeah. Appreciate it. Why is it so blur? Is it blur? Or is it okay?
I think it's going to take time for it to
Mm.
start.
All right. So do you have any questions? All right. So before we begin, let us talk about the exam, right? That's coming up. So for exams, right, in general, whoops, what's wrong with my, oh my God, no. This is bad. My Apple Pencil wasn't charged. It wasn't, oh, ouch. It wasn't locked for some reason. I don't think I can have a way to charge and talk at the same time, right? It charged very quick. All right. So sorry. It was not locked in properly for some reason. So maybe we resume in 5. Sorry. It charged very quickly. Okay. I hope so. Sorry about that. I didn't know. Not know. Okay, I mean, I guess if that's the case, and if you have any homework questions, whatever, we can talk about it while we wait. Yeah.
No problem for right?
There's no problem for
Yeah,
because
because you give the problem for just 3 and 5.
oh that so 5 is 4. Yeah, I guess I
Yeah, I just want to make
sure. I think when I numbered wrong. What is wrong here? connection. That's so weird. Why can't it recognize NumPy? Today, no, it's not a good day. My computer's malfunctioning. Does anyone know why it doesn't recognize NumPy? So weird.
Maybe try refreshing.
I did. It doesn't work. Refresh the kernel. Yeah, it just doesn't recognize NumPy. It says Python here. Yeah. Just somehow Apple decides not to work anymore. No module named NumPy. I'm connected to internet. Oh Lord. Oh, maybe I'm not running it. Probably. Still. Oh boy. Huh. It's definitely strange. Wow. Okay, somehow, yeah, my hardware just refused to cooperate. All right, 35%. I hope I'll have enough to talk through a lecture. If not, then I have to stop and recharge. Sorry about that. Okay, so yeah, so I want to talk about the exams first, right? So when I make the schedule, I did not recognize that the exam I made was on Thursday. So we'll have a schedule change to Tuesdays, okay? So in person. So I know the first one is scheduled for next Thursday. So I'll push it back, all right? So the first one, I'll push it back to February 28th, which is the Tuesday, right, in class, okay? So that's, and all the other ones will be similar, right?
Professor?
I'll announce the date again when it's close to it, and I'll change the syllabus when I get around to it.
Professor?
It's gonna be in person. Yeah, go ahead.
Is it Tuesdays or Mondays?
28th is a Monday?
I don't know, because we meet on Mondays and
Oh,
Thursdays.
sorry, shoot. See, thank you, Kareem. I am just losing it today. Apologize for the snow. So Monday, right? I mean, I do mean Mondays. Yeah, because we meet Monday, Thursday, so that's kind of confusing to me a little bit. All right, yeah, so I mean Mondays.
Monday is
Oh, Monday is 28, so I am right. Okay, thank you, Shinan. All right, cool. Okay, so how does the format work? All right, so I want you guys to do live code. All right, so meaning that there'll be a combination of theoretical and but the code will be, I would say, something like 75%, right? So theory maybe something like Eos Formula, that kind of thing, right? I don't know, right? Things that basically like the homework, doing some theoretical calculation. But I recognize that, right? The homework asks you to do more on the coding side. So correspondingly, the exam should also be on the coding side, right? So code, what kind of coding questions you should expect? Similar to homework, right? Some kind of simulation, some kind of, Monte Carlo simulation, numerical procedures, that kind of thing, right? Numerical calculations, even accessing some data, right? Maybe. So all the skills that you've done on the homework, right, will be on the exam. That's why I say that you must, right, master the techniques of your exam well. Now, what's the rules? The rules is, you bring your own laptop, right? Bring your laptop because it's live code, right? And then you will upload, right? Upload your results after class, right? So there'll be two pieces, right? The theory piece and the coding piece. Just like the homework, right? I will kind of make it clear which question's theory, which one is code. You can use, right, any materials you want. I don't care. Meaning you can reuse the code from your, homework. You can use the code from a solution. You can Google the code online, Stack Overflow. I don't care, right? You make the code run, that's good. That's real life. Well, the only thing that's not real life-ish is you cannot collaborate, all right, with anyone. So, well, that's why the point is in person, right? So I'll sit at the back, make sure that you guys don't pull up some weird chat or something to collaborate, which I doubt. But all right, so you cannot collaborate with any friend online, in person, whatever, right? You do your own code, but however you write the code, as long as it runs, I don't care, all right? I mean, of course, it has to run precisely and presentations will count, right? But the point is you must master the skills. Okay, so that's why it is. I will try to make it similar to the exams in the kind of contents, right, that you have to do. Okay, probably highlight the Monte Carlo simulation part, right? Numerical calculations part. Less on this, but still, right? We've done some of that. Maybe I'll ask you to post some data, whatever, just to make sure you can do it. So that's how I envision the exam. Any questions on that? Any objection?
I have a quick
Concerns?
question.
Yeah.
Approximately how many questions will we be asked to do?
Well, so that right, that Kareem would probably be not quite clear because I haven't written the exam yet. So how to say this? I envision it to be like probably around four questions, like the homework, right? Like the homework. So yeah, one theory question, 3 code maybe, right? Each code might have 3 parts. Okay. So that means that you should be able to, if you see some questions like the homework, you should be able to do it around 1 hour, 20 minutes, right? For the code and for the theory. Does that answer your question?
Oh, yes, thank you.
I don't know yet, right? And again, I mean, it will be, if it turns out to be too quick, right? You don't have time, well, so be it, right? The class will perform in a similar way as you, so I'll take that into account, right? But I do intend for something like homework, right? To be, again, these will not be new questions, right? There will be variations on homework ideas. Make sure that you understand what you've done so far, right? I mean, to give you a taste of, say, suppose I ask you to, I give you a iron condor, right? I ask you to find the probability it will expire in the morning with some parameters. Okay, write some simulation for that. Does that make sense? That will be something like question like that on the exam. So simulate it, right? Simulate the, I might give you some new process to simulate, right? But if you understand the idea of simulation, you can just do it like before. So yeah, I mean, I might be able to answer some questions on the exam, but right, of course, not to give unfair advantage to anyone. So things like that. But so again, right, the point is you must master this kind of skills, right? You must be able to do it live, right? So make sure that, you know, you guys know it. Is that okay?
Yes.
So right, make sure you can code your homework well. We're good. So yep, so the first exam will be February 28th, right? Bring your laptop, make sure it doesn't have some stupid problems like I have today for whatever reasons. If you cannot run NumPy, then you're in problem, right? I don't know why my NumPy doesn't run. Anyway. Okay, so let's begin our lecture then. So last time, we were discussing, right, the idea of the Ito integral, right, and how that's connected to the Ito's formula. So I kind of mentioned the Ito's formula kind of quickly because I think Professor Larson asked me if I cover that, right? Somehow you guys are using it in computational finance, but let's just go back to this and kind of mention it more carefully, right? So the idea is when you want to do something like this, let's say the integral, right, of some process, DWS, the idea is it's going to be some limit, right, as delta t goes to 0 of the Riemann sum. So that's really it, and that's really the miracle, right? That basically the point you have to pay attention to is that this must be the left-hand point, right? But we have a lot of discussion about how this guy is not differentiable, right, and all that stuff. The only point is to highlight is the calculus here will be weird. But in terms of, let's say, simulation, at the end of the day, you still do this, right? The weirdness, the strangeness show up somewhere else, right? The strangeness shows up in, I would say, probably two places. Choice of, let's say, this, right? And your homework asks you to verify that. In other words, right, for the Ito integral, whether you choose this or you choose this, it will converge to a different limit. But for the regular process, meaning if this is a differentiable function, then it doesn't matter if you choose left-hand point, right-hand point, the convergence will be the same. It will be converging to the same limit, right? So that's the first strangeness, okay? The second is in the calculus. Do you hear a question? Okay. So the second one, right, is in the differentiation. All right. And you also have a question in the homework to demonstrate this. For example, you should recognize that, let's say, something like this, right? What would this be equal to? Well, if you haven't done your homework, what would this be equal to? Well, this is just a U sub, right? This is a U sub integration because, right, you let U be sine t, then du is d sine t dt, right? You usually do this anyway, right? But this is really sine prime, right? Sine prime, right? So, but sine prime, right? So this actually is d sine t, right? Do you agree? That's all these are fancy ways to say the same. So these are just fancy way to say if you use sine t, then use d sine t. But this makes sense, right? The catch is it makes sense in terms of the dt integral. So in other words, this is just the integral from 0 to, I don't know, right? If you use sine t, then this is going to be inverse cosine, inverse sine of t, whatever, right? But it's u du. So that's u squared over 2, right? From there to there. Anyway, right, the whole thing is a long-winded way for me to say that this will be sine t squared over 2, right, which is by u sum. On the other hand, right, when you do this, which is a Ito integral, what is the result? Well, if you look at your homework, the result is this. So where is the strangeness? The strangeness is this extra factor of minus t, right? That you don't see. By the way, right, there's nothing special about sine here, right? I can plug in any differentiable function. I can plug in any differentiable function, right? And I will get this. As long as f is differentiable with respect to time. As long as something like this exists. You understand? So again, right, the fact that you can verify this on your code, right? That's why I was trying to code, except my NumPy doesn't work, shows that WT is not differentiable, right? And then you are asked to make a different choice, right? So I didn't ask you to pick the right-hand choice because that doesn't seem to be popular, but you pick the midpoint, the average. That's called the Stochastic integral. And if you pick the midpoint, then you do get to this part, okay? Without a minus t. But that's not the Ito integral that we deal with in finance. That's Stochastic, that's dealt with in engineering. And you can guess why. Because in engineering, they like to, TI plus, right? They like to preserve the classical calculus, but they have less concern about this flow of time. Okay, than us. So for them, right, when they deal with physical stuff, controlling, right, having something that acts like classical calculus may be more of a priority. But anyway, right, this is just so you know the strangeness of the calculus, right? But of course, we stick with Ito integral in finance, so we learn Ito's calculus, all right? But these are the strangeness that you should be aware of when you are in this territory. And you should know where the strangeness comes from or why we pick the left point, right? The motivation is, again, not to look into the future. Because at any point, right, if you think of this as your portfolio, then this is your number of shares held in this time interval. And you cannot, right, look into the future to know what future value is to form your choice. For example, right, the Stochastic integral requires you to know the future value of WT to form this choice, which in finance makes no sense because you cannot peek into the future, right? So the legacy of this calculus comes also has a financial interpretation. All right. So that's what I wanted to highlight. Questions so far? Now, another, right, I want to say is this. that so basically when we say this limit, right? The reason why we talked about it a lot is that basically it does not converge pathwise because it's not differentiable, but it converges in the L2 sense or in the mean square, right? This is in mean square or L2 sense. Anyway, you know, so when you take the expectation, right, of this minus this square, it'll go to 0. But so, right, that's the sense that it will converge to. So let's write that down. Again, right, this is a piece of technical thing that you don't need to be super concerned with, but you should be aware of that. So this is why, right? This is why you can use a Riemann sum to approximate that mysterious object, right? So anyway, the way you think of it is this is mysterious, meaning there's nothing that actually in real life you cannot get your hand on this object. All right. If you want to get close to it, the only way you can get to it close to it is through the Riemann integral, right? So simulation wise, this is the only thing you can do, right? The theory tells you that there is a number, right? There's a random variable such that this guy will get close to in the mean square sense. But you know, you can only get it right through the approximation. This is actually not as strange as it sounds. For example, you guys have been using pi, right, casually. But does anyone have the actual value of pi with them? The answer is no, right? We have always used approximation. I don't care how many digits you write, right? Even if, you know, 1,000 digits or so, that's still an approximation, right? The actual number pi is a, you know, for lack of a better word, right, a mysterious object that we can only approximate as close as we want. As long as we can define that sense of approximation, right? As long as we make it precise, then we just go ahead and use the approximation as a stand-in for that mysterious object. Is that okay? But that doesn't mean, right, that we cannot discuss the properties of that object, because by the word mysterious, by the way, right, I just mean that it's not something that you can get your hands on directly, right? It's not like, you know, it doesn't need to be worshipped or anything like that. But you still need to topple the property of that object, because the point is actually, right, even though it's mysterious, we show that it exists. Okay, we can define it. Is a legitimate object. Okay, it's not contradictory. That's what this means. For example, right, with pi, you probably have a bunch of properties that pi, you know, satisfies. Well, the most important properties is that the area of the circle, right, is pi r squared, for example, those kind of things. So this object, right, will also have a property, right? So this actually, now that is well defined, that's all we want to say. Meaning we are confident that there's such a thing. And it's a process, right? It's a stochastic process, meaning it's random. All right. So by the way, right, what does stochastic process mean again? It means that, right, first of all, it's a function of time, right? You can graph it, right? You can graph it. By the way, when you graph the stock price process, you are graphing something like this to begin with. Why? Because of the Black-Scholes model, right? So you are graphing something like this as well. And second, right, stochastic means that it's random, right? There are two ways you can look at it as randomness. Fix a t that is a random variable. You should think about that. But second of all, right, what it means is every time you run the scenario, you get a different paths, right? So that's why, for example, in simulation, you're asked to simulate many paths, because these are like scenario analysis, right? It's stochastic. So every scenario of history will give you a different path of the integral. Why? Because the Brownian motion will result in one path. Your integrand, if it's also random, will also result in a different path. Does that make sense? Okay, so it's just a stochastic process. On the other hand, the good news is it's adapted to the filtration generated by the Brownian motion. Well, this is just a fancy way to say that you know this object completely if you observe W on 0 to t. All right, which actually is a property that no one would really feel surprised, but actually you want that, right? So think about simulation, right? If you simulate the Brownian motion on this interval, if this guy is determined by the Brownian motion, for example, it is the Brownian motion itself, right? Or the Brownian motion square, whatever. Then, right, think of how you run your simulation. You just form the Riemann sum, and you would know completely what the value of this integral is, right? Otherwise, how do you output it? So that's all it says. But, right, on the other hand, there's something that we can say about this, about its properties. So first of all, right, by saying this, like I said again, that it's a random variable. So we should be able to say something about this random variable, or we would like to. And so some of the basic properties should not surprise us as the following. This random variable has the average value of 0. And where does it come from? Actually, it comes from the average of the Brownian motion, right? Differential is 0. By the way, right, all of these are kind of like not that super hard to look at, but if you want to prove it, it still takes some time, all right? So don't underappreciate it. Second, the second moment, right, of this guy is something that you know, which is all right. So this comes from by the way, right, I put this in quote because, now that if you do rigorous math, then you know that this object does not exist, right? There's a limit, but of course, right, we think of it as the differential when time is very small. So that's the motivation, or that's actually the intuition. This actually comes from, you guessed it, this, or that's actually what we say here. This comes from the quadratic variation property of the Brownian motion. So that's why we spent some time discussing the quadratic variation, because it influences the second moment of the integral, right? Also pay attention. So what this says is that this, okay, so this is a random variable with mean 0 and variance like this. Okay, notice that this is a completely deterministic object, or this is a constant. Why? Because they have an expectation here. It's very easy to, in the abstract, to casually drop this. But if you drop this, actually it's wrong. The reason is because this guy can still be random, right? Like, again, think of it as Brownian motion. So, right, there is an expectation inside here. So in some way, it's like we pass expectation inside. But the reason is because, right, or if you just think of what object you're looking at, this is the second moment. So it must be completely deterministic. Okay. And so these two properties together actually just implies that the variance of this object, right, is this. Okay, so far. So these are actually the only two universal properties you can say about the Ito integral, right? So this is two universal properties of the Ito integral. There's one more, but we need to specialize. If phi is deterministic, and deterministic in this context, you can think of it as only a function of time. All right, and not of the prime motion. Because right in this context, the only random source that generates all these randomness is prime motion in some way. So if something is deterministic, doesn't mean there has to be a constant, right? Because if it's a constant, it's so trivial, right? Something like this. What would this be equal to? Well, by the way, right, the rule for the integral of the Ito integral applies in the same way as the usual integral for the trivial case. For example, the constant still factors out, okay, which will become, so there's nothing to talk about, right? I mean, you know completely what this is if the integrand is a constant. So the word is not constant, but deterministic, meaning it's not a function of the prime motion, right? So deterministic really means that all the paths, right, are the same, right? Doesn't matter how many times you run it, it's the same path, right? Because it's not random, okay? So for example, right, if you want, an example would be something like this, right? These are all deterministic integrands, right? Because there's no prime motion in this part. Every time you run it, it's a single path, right? Same path. Well, if it's deterministic, what can happen? Of course, right? The statements above we made are true in general. So it's true for these. No surprise there. But what's surprising, or no, what's the additional statement we get is that not only that they have these kind of moments, but the integral itself is a normal random variable. Okay, with what kind of mean? Well, of course it has mean 0. Why? Again, right, from point 1. What kind of variance? Well, it has variance this. Why? From point 2. Notice though that from 2, right, I have dropped the expectation. I do not have expectation here. Why? Because phi is deterministic, right? I don't need to take expectation. Expectation of phi is phi itself. All right, any question? So for example, right, the integral from,
Do we not,
yeah, go ahead.
for the
What's the
variance,
question?
yeah, for the variance, would it not be like that integral times whatever variance that, like times t, since, or dt, since there's like a variance?
There's a variance. What are you asking?
Like further down when you say,
I know you're asking for this term. Yeah, go ahead.
yeah, why is
I
there
don't
no
want to
like
read.
t term in the variance?
Why is there no what?
Why is there
No
no
t?
like t in the variance?
Right here, right? Or unless you didn't see my notation.
Oh, okay.
Remember, right? This is not a simple something like t times something, we are in a context where things are moving with time, right? So distinguish between this kind of constant and the concept of deterministic. All right, deterministic doesn't mean that you have to be constant in time. Deterministic only means that you have to be constant in scenarios, right? In random events. Therefore, to compute the variance, you still have to integrate it in time. Except that now, right, you do it with the quadratic variation of the Brownian motion. Does that make sense?
Yeah, thank you.
Yeah, there are a lot of new things here, right? Basically, it's a new calculus in some way that's consistent with the old calculus, but that's why you got to pay attention to each of the pieces of the information and know where they fit in, right? It takes a while. So for example, right, this guy will be a normal random variable with mean 0 and variance t squared over 2. Right? This guy will be a normal random variable with mean 0 and variance e to 2t over 2. No, right? I should stop doing the over 2. E to 2t, right? Minus 1, right? Even. Yep. Wait, hold on. Is that over 2? There is, right? Because when I integrate, I'm just integrate quickly in my mind, but this is e to 2t, right? Over 2, right? So yeah, there is over 2. E2s, right? Okay. By the way, right, you also can test these things with simulation. How? By generate, right, a lot of these random variables, right? So generate a lot of paths, and for each path, right, record this value, and then do a histogram, right? I think you are asked to do that on one of your homework questions. So for this, right, you can see that this will look like a normal random variable when you record all, like a lot of the values, right, of this integral. All right. So now, so that's the integral itself, right? That's the integral itself. Now to demonstrate to you, right, how this fits together, let's think about this. Does this integral, right? By the way, this is one of the easiest example we can think of to work around these things, right? So does it have a normal distribution? Why or why not? There are many ways you can answer this question, and they all fit, okay, together. Yes or no? No?
No, it doesn't.
Why not?
Because it's equal to like t squared term.
Okay, great, right? So first of all, if you remember the answer I gave, however I got it, right? It is WT squared minus T over 2. And WT squared has what kind of distribution?
It would have like a chi-square distribution.
Yeah, like chi-square, but I think in this case it will be a gamma because of the T, right? Chi-square require you to have a 1. Yes, that's correct. So that's why it's not normal, right? But also, right, this is consistent with the above. Why? Because is this a deterministic integrand? No, right? So therefore, this is consistent that with the above, that it does not have a normal distribution. Okay. What is the expectation of this guy? Well, of course, from the above, you know there should be 0. But let's just test it by looking at our formula, right? To at least make sure that it's consistent, because if somehow, right, we claim that these guys are equal, but if you take expectation and they're not equal, then, well, our formula must be wrong. Is this expectation 0?
Yes.
Yes, right? Because WT square exactly has expectation T is the variance of WT, right? So that's correct. So at least that's consistent. Now comes the even more interesting piece of the variance, right? What's the variance of this? Well, let's use item 2 right above. Again, right, this just demonstrates to you how all these guys fit together. Item 2 says, right, that this is the integral 0t of what? What does item 2 say? Should be S ds. Right? Because it's the expectation of this square ds. But expectation of ws square is s. Agree? So here you go. All right. And so it is s square, sorry, t square over 2. All right, so that's easy enough. But that's not just the only point, right? The only reason why we want to calculate this. Again, right, the big idea is we claim that these are true. So we can also take the variance of this, right? And it better be t squared over 2. Now that's interesting, right? How do I take the variance of this? How do I take the variance of that? What's the first step? Did anyone say something? Well,
Okay.
so you would do the obvious first, right? You would factor out 1/2 and you would drop the constant t. Okay, so now tell me how to proceed. How do I take the variance of WT square?
You can rewrite WT squared as T times standard normal squared.
Square root of t, right? That's very good, but it's square root of t, right? Because it has sorry, So this square, I mean, if you mean WT, then it's square of T, right? Because the variance T, right? Don't forget that.
Yeah, but then you square it, so it'd be T times.
Right. No, you're right.
Okay. Yeah,
Agree. I don't know if you said T or WT, but yeah. So this will factor out as T squared, right? Variance of standard normal square. Okay. Almost there, because, right, that looks very promising. What that means is, what is this number? If it's consistent with the above, this number must be should be
2.
2, right? Well, can we verify that? How do we calculate this piece? Well, we have nothing better to do but to use the formula, right? What is this? What is this piece?
1.
Yeah, that's 1. So this piece must be
3.
right. Now, so we're kind of like working backward, right? But does anyone know for sure that this is 3? Because that's the point, right? We want to show forward, not backward. But anyway, do we know this is 3? In fact, right, fun fact, what are these two quantities for the standard normal? What are the odd and even moments of the standard normal? Anyone knows? Well, if you work with Brownian motion, you should be very familiar with standard normal, right? Because that's the source of Brownian motion. So these are good knowledge to have, right? If you work with Brownian motion. The odd moments of the standard normal is 0. Why? Because when you do the integral of something like this, you get 0. Because this is an even function. This is a odd function. So when you integrate over the symmetric, right, even though infinite, so something like this, right? I don't know if that's the picture, right? But something like that, when you add up, you get 0. I mean, it's almost like this. What is this integral? That's 17, by the way. I mean, to make it even more weird. Do you need to do calculation here? No, you don't, right? It's a symmetric interval. It's an odd function. So it's something like this. You add up, you get 0. The only difference, though, between these two examples is that if you go to infinity, you better make sure that your entire mass on each side is finite. Because if you run into infinite minus infinite case, then you're in trouble. But this guy will help the mass to be finite because nothing grows, right? I mean, it decays very quickly. This is a polynomial, so you're fine, right? Anyway, that's a very easy reason why, right? This guy actually is fun. For example, what's expectation of z to the 8th? Anyone knows? It'll be something like that. I think they even have a notation for it. I believe they call it something like this. So it's I think it's called a cumulant. Never mind the name. Basically, you take the number and you skip 2 instead of skipping 1. It's like factorial, but skip 2, right? So basically, if we trust this notation, which I think is fine, you get that. You just keep multiplying the odd numbers down to 0, down to 1. And that's why, right? Z to a 4th is 3, because it's the first one. It's 3 times 1. Now, how on earth does this happen? Well, it's easier than you think. Let's check out Z to the 4th. Actually, let's check out this. Check out this. Right? Suppose you want to calculate this. Well, how on earth can you calculate this? Well, the answer is you don't, right? Of course, there's this guy outside. You don't, but you try to cleverly reduce the problem by, first of all, combine this into a object where you can integrate, right? And then what's left is something you can differentiate. Because, right, so does anyone know what technique we're using here? Integration by parts, right? If you integrate this, it turns out that this integrate to be exactly this again with a minus. But it doesn't matter because infinity to infinity still get 0. So after all the dust settles, you'll get 2k minus 1 outside, and then z to the 2k minus 2. Easy. Okay. So what have we concluded? We have concluded that expectation of z to 2k is 2k minus 1. Expectation of z to the 2k minus 2. And this is called a recurrence relation or recursion, where, right, the base case is 1. Combining these two, you will easily obtain that. Any question? All right, so that's just a fun aside from probabilistic knowledge. But right, I mean, all in all, this is just a fun example to demonstrate that, right? All the observation above makes sense, right? But notice now it opens up a wide horizon for you to look at things, right? Dealing with normal distribution. So it's fun to play around with this and ask all these kind of connecting questions, right? You might see something like this on the exam. Who knows? Question. All right. So it's all fun and good, right? So notice that all the above, right? So our going to example is this, right? So all the above shows that there doesn't seem to be an issue with this claim. But that doesn't mean that it's proved, right? Why? Because all I show is that these two random variables agree in their expectation and their variance, right? That doesn't mean that they're equal. It just means that this claim at least is not proven false yet, right? So if I want to prove this to be completely true, right, beyond all doubt, well, there are two ways. The first way is to take all the kinds of moments, right, up to infinity and show that any moments are equal, which probably is super painful, right? But the second, of course, is the Eos formula, which is the source, right, of where all this comes from. Okay, so to repeat, to prove that this is true, right, the source of it is Eos formula, right? All the above that we did was playing around with the properties of the Ito integral and kind of show you that at least these are consistent. Nothing's blatantly wrong, right? But to show it's true, you have to do Ito's formula. It's almost the same as saying this, right? I mean, if you want, suppose that you want to convince, I don't know, a middle school student that this is true, you know, then you ask him to check that for t equals to 1, this is 1/2. For t equals to 2 is 2, that kind of thing, right? And then you show him for several values that this is true. So he kind of believes you that it's true. But of course, to show that these guys are true in general, you must show that it's true for all t, right? Which can only be shown in the abstract. You cannot check numbers. Anyway, so with Eos formula, right? The goal is actually go from the left to from the right to the left. Eos formula is like differentiation, right? So we think of antiderivative because you are trained with calculus to do so. But in fact, right, before you do antiderivative, you were taught derivative, right? So it's actually chicken or egg, but actually it's more robust to teach integration first and then differentiation later. Anyway, right, so these two are two sides of the same coin. We've been traveling on this way, meaning we say that there is some object like this, and it has, you know, in some cases we can write down, right? By the way, this is the explicit formula, right? This is the antiderivative of this integral. Okay. Now, so to verify that, we need to go backward. In other words, notice that, right, what we're claiming here is something like this. Differentiate, right, the above. Then what we're claiming is that the differential of this is the differential of this, which is WT dt, dWt. Okay, so far. So this is like the differentiation, but it's very basic one, at least for some objects, right? The differential of this is just this. Why? Because like I showed you last time, right? A small gap, right? A small movement of this. Right? Is this. Which is approximately WT dWt. You understand? So this is the reason. Now, what do we have on this side? Well, on this side, right, then we have the 1/2 can come out. Then we have this, and we have this. Agree? So again, right, don't feel too weird about D. D is like a differencing operator, right? You just take the difference, like, difference in stock price, difference in time, that kind of thing. So D is just a difference operator, right? So that's why it works like that. Now, if these two objects are equal, then if you take the difference, they're also equal. In fact, right, what we're claiming is something like this. dWt square is, right, 2Wt dt plus dt. Sorry, 2Wt dWt, right? And that now looks more like Eos formula. Why? So remember, right, the goal of Eos formula is to take a function of time and ground motion and ask, if I differentiate it, what do I get? All right. So again, right, the answer has been given to you last time, right? The answer was f sub t plus 1/2 f sub xx dt. This is f sub x dwt, right? The answer has been given to you last time. But you see, right? So that's exactly Eos formula in action. Now again, let's get into a context, right? You can do the formula. You must be able to do the formula, but it's better if you understand the idea, what this formula is trying to tell you. All right. Again, the easiest thing is to go back to calculus, back to classical calc, and try to understand the idea there. From classical calc, right? Let's say you have something like this, right? F of t is t squared, right? Now, then, in calculus 1, right? Some enlightening professor teach you this, right? This is going to be 2t. But that teacher should also have taught you the meaning of this formula. What do you mean by this? Well, if you remember, right, this one is also called f prime of t. And f prime of t, by definition, is limit as h go to 0 of f of t plus h minus f of t over h. Right? So now instead of h, we call it dt. And so you see that, right? All these are just a fancy way to say, as time moved a little bit, right? As time moved a little bit, how much has my function moved? As it depends on time. This is a classical relation, right, in physics, right? As time moves, how has my position moved? How has my position changed? Which, of course, the answer in physics is velocity, right? So all these are just rigorous math to make sense of that relation. Okay? So that's nothing that's strange, except that you have been doing it in a formulaic way. So you might feel strange if people write like this. But of course, I guess in Newton's time, maybe they feel more familiar with this than this. Because for them, right, exactly, time change, position change, velocity, right? Now, so when it comes to Eos formula, is it strange? Well, no, right now you know what happens. Because what do I mean by this? So now, right, I will improve classical calculus by saying that I have an extra dependence. But notice, right, this extra dependence is very funny. Technically speaking, the whole dependence can be viewed as dependence only on time. Why? Because Brownian motion is also a function of time. All right. So if you want to kind of go out of this black box and just view it as a process in time, you can. But this structure here is a little bit more structured, if you will, right? The dependence on time is broken down in two pieces. There's a regular time dependence, and there's a more sophisticated dependence of time based on Brownian motion. So again, right, as time moves, how does my process move? So that's actually a very reasonable question to ask, just like classical calculus. Except you know that this cannot be answered. The reason is Brownian motion is not differentiable. So you cannot capture the change of Brownian motion with the change of time. All right, so in that sense, you cannot do this. This will never capture this relation. Or if you will, the velocity of your process is not defined because it depends on Brownian motion, and Brownian motion is super rough. Therefore, to capture a movement, right, of your process, as time moves a little bit, your Brownian motion also moves a little bit, right? And combining these two together, you will capture the change of your process. That's all, right? So it's very intuitive. I mean, at least, right? That's what it's trying to do. And of course, right, to know what these two question marks are, is these two, right? Okay, so far? All right, I know that time's almost up, so let me continue, right? So let me try to write something out. Now, that by itself, though, does not completely explain Eos formula. So far, I've just tried to explain what Eos formula is trying to do. I haven't explained why, right? The pieces that fit into Eos formula are these pieces. Where do they come from? Okay. So again, actually, it comes from exactly the idea that, right, as time changes a little bit, what happens? So notice, right, as time changes a little bit, meaning that as you move from t to dt, right? Then basically, Brownian motion also moves to a new point, right? And so your process, which is this, also moves to a new point. So basically, when you want to ask for the change of your process, you're asking for this change. Now, if your function is well behaved, then the change of the function can be captured by the change of time and the change of space. All right. So this is Calc 3. It will be approximately the derivative in time, right? The partial in time of this function times the change in time, plus the partial in space times the change in space. The only surprising thing, though, is well, somehow there's still the second derivative here with the so-called change in space square. All right, because that's exactly what the final answer is. Right. So again, right, it's very intuitive calculus. To find the change in a function, you take its partial and times the change in the individual component. So far, so good. The only thing, not strange, but you would question, because everything here has to be precise, is why do you go down to the second level and try to capture the second, right, the square of the change in here? And the answer, actually, if you've been following the discussion so far, is not that strange. The reason is because dWt square is dt. So you need to capture that because it doesn't die, it doesn't disappear. On the other hand, why don't you capture, say, something like this, right? Because you go to a second level, right? In this, you also can go to a second level in the t direction, right? Why don't you? Exactly, because when you square this, is 0. So the dt is very regular. So you only need the first derivative to capture all the change. But the w is so rough that if you just capture it at the first level, you won't capture everything in the change. When you square it, you still see something to recover the function, right? But anything below that is 0. For example, dWt times dt is 0. Higher order term is 0, etc. Right? So I think we'll stop here. But that's the basis for why, right? The Eos formula captured this way. And again, right, notice that it's still harping back to the quadratic variation of the Brownian motion and the roughness of the Brownian motion. That's still the key ideas, right? And so I just want to make that connection. Okay, see you on Thursday. Sorry for the hiccup at the beginning.
Thank you, Professor.
Yeah, see you. Yeah, thank you.